subject of this talk will be what occurs to the gas molecules once they're inside the cavity of the zeolite, and not what happens. This is not a modeling of the Henry's law constant or the interaction between the particles and the zeolite surface. And just to further emphasize that, and also to point out that, well, many of the systems that I examine later in the talk will be inert gas systems absorbed into molecular sieve cavities. And in general, they display a Langmuir-like adsorption isotherm. The Henry's law part comes totally from the interactions between the gas molecules and the surface of the cavity. And whatever deviation there is from the Henry's law occurs due to the adsorbate interactions, or the gas-gas interactions. Now, before I get into my own work, let me review for a moment. The example of the review is the krypton molecular sieve 13X cavity. The data is available in the literature due to Rees and Williams, and I'd like to take a moment to discuss some theoretical work by Soto and Myers that will be relevant later in the talk. What Soto and Myers did was, following other researchers in the field, they calculated a Henry's law constant from theory, accounting for dispersion forces between the gas molecules and the cavity, and also, in addition to that, accounting for electrostatic interactions with the ions in the cavities. And then, to account for the gas-gas interaction, what they did was perform Monte Carlo simulations of the gas molecules inside the cavity. Now, they did two kinds of simulations. One where the molecules saw each other as hard spheres, and in another case where they saw each other as Leonard-Jones particles. Now, let me emphasize that the hard sphere molecules still interacted with the walls of the cavity through the dispersion of the electrostatic forces, but they saw each other as hard spheres. And then they added on the Leonard-Jones interaction that's using parameters from gas phase modeling of the krypton molecule. So the two theoretical curves show the effect of cooperative forces on the adsorption isotherm. The thing to point out here is that the calculation to get the gas-gas interactions, the Monte Carlo calculation, is not a very economical way to do calculation. And our motivation is to find a simpler way to do this calculation. Now, one of the things that motivated the model I'll show you in a second is the picture of the gas-solid interactions. Here's a typical picture of a krypton molecular sieve 13X interaction taken from Soto and co-workers. And what we see here is the interaction for a particular angular orientation inside the cavity. Now, as we look at different angular orientations inside the molecular sieve cavity, the gas-solid interaction curve is going to change due to the electrostatic, or due to the ions inside the structure of the cavity. But there's one major thing, or two major things to point out here. First of all, accounting for just the dispersion forces, we have a spherically symmetric potential inside the cavity. And it turns out that the ions, although because of the ions, we have quite a heterogeneous surface inside the cavity, the ions tend to just deepen to the minimum of the well and not really change the position of that minimum very much on the scale of the cavity itself. So this served as a motivation to look at the adsorbed phase as simply a spherical surface onto which the gas molecules absorb. So the adsorbed gas molecules inhabit this spherical surface. And if we imagine that the adsorbed molecules are hard spheres and they enter the cavity, then effectively, rather than hard spheres, if they're absorbed on the spherical surface, we can think of them as disks, but not quite two-dimensional disks. We can think of them as hard caps. absorbed on the spherical surface. Now I'm going to stay with this hard particle model and not examine cooperative forces for the remainder of the talk. I'll have something to say in the conclusions on that. But if we adopt this very simple model of rigid particles absorbed onto the spherical surface, then we can introduce a rather elegant theory from liquid state theory to predict the activity of the absorbed phase. This is scale particle theory, and it was developed by Rice, Frisch, and Lebowitz for hard spheres and later extended to hard disks. And we can very simply make the extension to this hard cap fluid. Now, I don't want to go into very much detail on the mechanism of getting the activity, but let me just say that what the calculation involves is imagining that we place a point in a fluid of the hard caps and expand this point, sort of scale it up, and if we obtain the work of scaling up or growing this additional particle, that is what scale particle theory is, and this operation gives us the activity of the absorbed phase. Now, I don't want to burden the audience with too many equations in a 20-minute talk, but one thing I wanted to show was that the equations are very simple and easy to implement. We get the activity of the absorbed phase simply in terms of geometric parameters and the number of particles in the system. And it's just an integral over a very simple function, which I've shown here. The results for the activity of the absorbed phase look like so. What we've done here is plot two cases. One, a 5-particle system. The dash curve, the dash lines, let me say, are the theory. We've taken two cases, a 13-particle system and a 5-particle system, and compared it to simulations done on the hard cap system. It's a fairly easy simulation to implement because it's a small number of particles and we can quickly get results and compare them to the theory, but it's a lot more satisfying to have a closed form equation for the activity. And we can see that the lines pass through simulated points fairly well. So we use the spherical surface scale particle theory model for the activity. Another thing to point out about this is that we see that the two curves with different number of particles at the same fractional coverage display different activities. And this is simply a small system effect. The number of particles in the system becomes a very important parameter of the system. We have to know the number of particles and the area of the system, not simply the density of the system, as one would have to know it for a macroscopic absorbing surface. The key point is this is a microscopic absorbing surface in relation to the particle size. Well, the absorption isotherm can be calculated simply now. We have everything we need to know. We have the activity of the absorbed phase from the scale particle theory, and we borrow from Soto and Myers their theoretical calculations for the Henry's constant, and we obtain the absorption isotherm. Now, this is the slide I showed earlier with the spherical surface scale particle theory model included now in the calculations. And it turns out that the theory to this point is not that predictive, does not have that very good predictive capabilities. But we see that the results fall right in between the simulations conducted by Soto and Myers for the hard sphere and Leonard-Jones molecules. We've gotten this result with a lot less effort than doing Monte Carlo simulations for each pressure, for example, or activity. So the message here is that at this point, the theory is not very predictive yet, but compared to what had been done in the past, it's a lot more economical a calculation. Now, there's a way we can make the theory more predictive by introducing one parameter into the system. So far, it's a zero-parameter model. What I've been doing to calculate the size of the absorbing surface is to take the minimum in that the radius at which the minimum in the potential well occurs. Instead of doing that, what I could do is use data on the saturation capacity of various zeolite cavities and use that to determine the size of the absorbing surface. It's a rather difficult problem to calculate the number of small spheres that could be fit just right on the spherical surface. But luckily that calculation has been done for us. It appears in the mathematical literature. And given the saturation density of a zeolite cavity, I can use one of these estimates for the size of the particles. The stepped curve are exact results, and I also plot two continuous curves that might be more convenient to use to determine the particle size for a given saturation density. So with this, we can calculate absorption isotherms again. And now I display an example of the krypton molecular sieve 5A system. And I compare the zero-parameter model where the cavity, where the radius of the absorbing surface is determined from the cavity potential minimum. I compare that to the saturation limit. The dark curves are best fit through data. It wasn't really practical to tabulate the data, but a best fit equation was available in the literature. So that represents experimental results, the dark curve. The saturation limit determination of the size of the absorbing surface is the dashed line, and the dot dash curve is the cavity potential minimum. Now, you see at the low temperature, 423K, the cavity potential minimum falls far short of the true absorption isotherm. At higher temperatures, it's not so bad. But when we introduce the saturation limit determination of the size of the absorbing surface, in this case, we get very good quantitative predictions with this very simple theory. Now, I'd like to say that we tested a bunch of systems, and I showed the best results here. There are a number of systems that don't give such good results, and the model has to be extended. Let me just review the assumptions we made, and they're rather severe. The first assumption is that we have a spherical absorbing surface, and this is the most justified assumption in light of the shape of the cavity gas potential energy curve. The second assumption is that we have monolayer absorption, and this definitely may not be true, and was the reason for failure for some of our fits. Thirdly, we can assume that we have a homogeneous absorbent, and fourthly, we have a hard sphere absorbate. Now, we don't pretend that the merit of this simple model is that it can serve as a prediction for many absorption isotherms, but it does, for very little work, give us adequate prediction in some systems. But what we do think, though, is that the merit of the model could serve as a reference onto which more realistic effects can be added. For example, perturbation theory can be used to relax our assumption of a homogeneous absorbing surface. We could introduce a heterogeneous surface, and also long-range interactions, such as the dispersion interactions. In this way, we can introduce the cooperative effects via perturbation theories. So the model can serve as a reference. Thank you.
Thank you very much. Any questions? Over here.
Yes,
sure.
The isotherms of Rees and Williams for krypton, which you showed, actually indicate in an almost linear path, or even a path with a slight inflection, upward inflection, that molecule-molecule interaction is important. I didn't see in the summary on the last slide any attempt to allow for this. in your model?
Introduce molecule.
Well, this could be the
Krypton,
cooperative code.
Krypton. What? Okay. Well, that's what I was saying in the end is that you're talking about introducing cooperative effects. That's right. The model, as it stands, does not introduce that. We just assume the rigid particles. But we hope that it can be used via perturbation theory approach that's often used in liquid state theory. Once you have the thermodynamic properties of a hard sphere system, it's easy using perturbation theory to tack on the effects of interactions between particles. So the work definitely needs extending in that respect.
Would you introduce something like the Lennon-Jones potential? You talked about that earlier.
That's right.
Not only between the molecule being adsorbed and the surroundings, but also between the molecules themselves.
Oh, exactly.
Separate Lennon-Jones.
That's what I mean. Exactly that. That's what would be the next step in the modeling.
There's another question right here. Go ahead.
I would have thought that your little model of the circular cavity with the molecules absorbed around it would be more useful in a pore size distribution examination than adsorption isotherm. In fact, I've got here 3 slides. Can I just come up quickly and show you?
You better make it fast.
I'll make it fast. Because in your work, the pore size argument you mentioned with the operating feature. If we have a pore like that in a material, we can work out the number of molecules in the diameter of the pores in that way, and then we can plot it like that. And the dimensions that I was talking about this morning of Vp over Vm then tell you immediately the average pore radius that you're dealing with, so that in pore size analysis of an absorption isotope, this idea is very, very useful. But I would have thought in your case, where you're dealing with an entrance to a cavity,
That's right.
that the entire, the critical factor would have been the entrance, which would have determined the point at which not capillary condensation into the pores.
Okay, I see what you mean. I don't think that's the point of my work, though, because the entrance of the cavity, that will affect the Henry's law constant. That's the way one particle gets into the cavity. And my concern was that I take the Henry's law constant as an input to the model. And this is what, it's just adapting Soto and Meyer's calculations for the Henry's constant. And they took that into account to obtain their potential energy curves for the molecule surface interaction. So once the molecules are inside the cavity, the only geometric parameter that matters is the size of the cavity.
Yeah.
Okay,
I've got one up here first. Go ahead, Bob.
In the scale particle theory, the normal presentation of that is that the reversible work of cavity formation is a power series with the term of power series and the ratio of the radius of the particle to the radius of the cavity.
That's right.
And the coefficients of that power series have to do with surface tension and the radius of curvature.
That's right.
I didn't see that.
Okay, I glossed over that point, but what happens is, instead of a power series in 1 over the radius of the cavity you're forming, you have a power series in cotangent of theta, the angle of the cavity that you're forming, the angular measure of the cavity on its spherical surface. All right, and the coefficients are involved with the work and surface tension, or the pressure and surface tension of expanding that cavity. But what you point out, though, is that in such a small system, though, it might not be justified to associate these coefficients with the forces or the surface tension in this cavity. But actually, in scale particle theory, it's a very small cavity that you're expanding, and they make the same assumptions. I don't think that's that critical in that case.
Probably pretty critical. In fact, that's the whole basis of scale particle.
Well, okay, well, if scale particle theory is wrong, then this is wrong. but it's the same. I think it's the same mistakes made here, or the same that is made in scale particle theory. And scale particle theory seems to work very well for hard spheres and hard disks.
You got one more question over here, quickly.
In that paper whose data you used the bar.
Yes, thank you.
So we did have to neglect the krypton molecules which were sitting in the windows, in the four windows. So you can't really assume that those are quite large windows.
Yeah, I know. But the dispersion forces and, well,